So, in our last class we have seen the electric field due to various distributions, point, ring, disk, sphere, hollow sphere, solid sphere, and we solved some problem based on the variation of the field. So, most of the problem we have done for uniform field till now, and non-uniform field, those problem we will take up later, right, after completing potential energy concept. So, our today's topic is potential energy. What is potential energy? So, change in potential energy associated with any system is defined as negative of work done by conservative forces while changing the configuration of the system. So, any system is there, if I change the configuration of the system, then whatever work conservative forces are doing, negative of that is defined as change in potential energy of the system. Let us see the definition first. So, the change in potential energy of system is equal to negative of work done by conservative forces to change the system, right. So, at any moment I can write work done by conservative force is equal to negative of change in potential energy, right. That means change in potential energy can also be written as negative of work done by conservative force, right. And we know the definition of work. So, if I integrate this one, then I will get change in potential energy, right. So, work is nothing but F dot force dot displacement, right. So, simplifying this one will give me the expression change in potential energy is equal to negative of work done by field. Work done by field can be written force by field dot dr, right. And if we are changing the system in such a way so that the constituent of system are not gaining any kinetic energy. So, from work energy theorem what we know that work done by external agent changes the mechanical energy of the system. So, mechanical energy of the system is nothing but kinetic energy plus potential energy, right, change in potential energy. I can write it this way. If system is changed in such a way so that the constituent of the system not gaining any kinetic energy or there is no appreciable change in the kinetic energy, then I can write work done by external is equal to change in potential energy. So, change in potential energy can also be written as work done by external. Change in potential energy can also be written as work done by external, but with condition that there should not be any change in kinetic energy. So, the whole expression I can also write this way, that change in potential energy is work done by external agent to move particles from one location to another location provided there is no change in kinetic energy of the system. So, out of these two definitions you can use any definition to get the change in potential energy of the system, right. You can go by work done by field or you can go by work done by external agent, right. But when you are going by this definition, then you have to make sure that there should not be any change in kinetic energy, right, and there is no such condition required in this situation. There is no such condition required for this situation, right. So, we will use this definition or this definition to find the change in potential energy of the system. So, I hope the change in potential energy definition is clear. The change in potential energy of the system is equal to negative of work done by conservative force to change the system, right. Now let us see. So if I take two charge particle system, so now here our system is two charge particle system and I want to find out the potential energy associated, right. So what is the potential energy associated when right now this distance is say r. So what I can do, I can move this particle from here to infinity or from infinity to this point to get the change, and to get the change I need to find out either work done by field negative of that, or I need to find out work done by external agent, but in that situation there should not be any change in kinetic energy, right. So I can go by work done by this force or I can go by work done by this force, right. When I want to find out the work done by this force, this Ex means external. So right now this is at rest, so this particle is exerting force on this particle, that I am calling field force. To hold this one at rest, I need to apply force in opposite direction, right. Right now it is at rest and this one is fixed, so this one is fixed, right. So this is held stationary, fixed. I am moving only this charge particle so that mathematically it becomes simple, or you can move both the particle, they are initially infinite distance apart and you can bring them at distance r, or you can do reverse, that initially they are at distance r and then you are moving it to infinity, right. So here I am assuming that initially they are at distance r, I want to find out the potential energy for this configuration, and then to find out the potential energy at this configuration I am moving this particle from here till infinity, as when they are at infinite distance apart the potential energy associated with when they are infinite distance apart is 0, this we are taking reference. So this is reference, so I can use this reference, right. So this is our reference. So this is held stationary and initially this is in equilibrium because this force is equal to this force. So field is exerting force on this particle in this direction, to keep it at the same location I need to exert force this way, and both the forces are equal. If I reduce my force slightly, so this force is little less than this force, then particle starts moving in this direction. As the difference of force will be very small, the acceleration will be very small, the gain in kinetic energy will be very small, that we can neglect, right. So when I am using the definition work done by external agent, there is no appreciable change in kinetic energy, and you can find out the change in potential energy using the definition what we have in previous slide, right. So if I want to go by this definition, because this is simpler, right. So work done by field, if I can find out, I will put minus sign in front of it and I will get the change in potential energy, right. Let us see what happens when I move this particle from here till infinity. So as you move this particle to infinity, this is exerting force in this direction and you are reducing your force in such a way so that it is slightly less than this one, right. So as particle moves, what happens, as particle moves, this force reduces and this force also reduces. When it goes to infinity, this force becomes 0, and at that time your external force is also 0, right. Let us see once again. So I am applying force in this direction, my force is little less than this one, so that it will allow particle to go in forward direction, right, without any appreciable change in kinetic energy. So you can see as it moves, I am applying force like this, my force is slowly getting reduced because the requirement is getting reduced as it is moving away. So, for any general distance r, if I further move this one by dr, if particle further moves by distance dr, then how much is the work done by field? So, we know work done by field is negative of change in potential energy, right. Just now we have defined change in potential energy. So, work done by field is nothing but force by field dot dr. As the field force and the displacement both are in same direction, this dot product cos dot product A vector dot B vector is equal to mod A mod B cos theta. So, cos theta, theta both are in same direction, theta is equal to 0, cos 0 1. So, this dot product will become 1, right. So, this cos 0 will be 1. Now, I will substitute the value of force, right. So, when it is at distance r, this particle is at distance r, force of interaction between these two from Coulomb's law, k q1 q2 divided by r square. So, I can write k q1 q2 divided by r square dr integration. Now, I can use reference. Reference is potential energy at infinity to be 0. So, when separation is infinity, then potential energy is 0, and I want to find out the potential energy associated with this system when separation is r. If I integrate this term, look at this one, 1 upon r square will give you, integration of r square, this is nothing but minus 1 upon r after limit, we can write this. So, limit is r to infinity. So, 1 upon r with minus sign when you write, using upper limit and lower limit, simplifying, you will get u is equal to k q1 q2 divided by r. So, two point charges at distance r, the system will have the energy, interaction energy, which is k q1 q2 by r. So, because of the interaction of these two charge particles, the system will have potential energy, and that potential energy we are defining as k q1 q2 divided by r. So, we use the basic definition of change in potential energy, that work done by field is equal to negative of change in potential energy, and using that we got this expression. So, for any such system you can use this expression k q1 q2 divided by r. So, even if there are multiple charges in the system, for example 3 charges, 4 charges or 5 charges, in all these cases you can use the combination of 2 charges and you can use this formula, energy scalar quantity you can directly add. So, for example, if there are 3 charges in system, 1, 2, 3, so there is one combination here, there is another combination here, there is another combination here. So, writing potential energy associated with this interaction and this interaction, adding them, you will get the total potential energy associated with the system, right. I hope this formula is clear, right. Now, let us see one example. So, I hope this is clear, right. Let us see one example based on this expression. So, question says there are 3 point charges q, 2q, 8q, and they are to be placed on 9 centimeter long straight line. So, all 3 must be placed on a 9 centimeter straight line. So, first, second, third must be placed on 9 centimeter line in such a way so that potential energy associated of the system should be minimum. We want least potential energy with these three combination. So, to have the minimum potential energy, one thing is clear, that these two, which are the largest one, must be kept at the larger distance apart, because if separation is less, K Q1 Q2 divided by R, if separation is less, potential energy associated will be more. And one more point, now here this is a scalar quantity, potential energy what we are talking, that is a scalar quantity. Here charge must be placed with sign. So, in this expression these all charges are with sign. So, if both are positive, then here plus will come, assume that both the charges are positive. So, I will write it this way, plus Q1 plus Q2 divided by R K times. So, this whole expression will be positive, right. Positive sign here says that force is the repulsive one, and if one of the charge is negative, for example now I am considering minus Q1 and plus Q2, I want to find out potential energy associated with this system, then the potential energy associated with this system will be U is equal to K, I will write charge with sign Q1 and then Q2 divided by R. So, you can see this minus sign will come in front and this whole value will be negative. Here negative means it is, or interactive force is attractive in nature. So, in potential energy expression these charges are kept with sign, and I already told you that when you are writing electric field or force magnitude 1 upon 4 pi epsilon naught Q divided by R square, this is without sign. But when you are writing field in vector form, direction will be taken care only if you are writing this charge with sign. So, in this situation when you are writing vector in vector form, this charge has to be with sign. When you are writing vector in magnitude form, then charge will be without sign. When you are writing scalar, then charge is always with sign. So, keep that point in mind, because most of the students commit mistake while writing the potential energy expression. So, I hope this point is clear. Let us first erase. Now, let us get back to the question. So, we require minimum potential energy and all the charged particles are positive. So, minimum energy of the system will be when these two largest one, they are at the maximum distance, right. So, I need to place these two charges at 9 centimeter distance, and in between I need to place this remaining charge. So, 2q and 8q must be kept at the largest distance, and in between I will place q charge, but I do not know the location, right. So, what I can do, I can place that q charge somewhere in between at some distance x. So, I do not know the value of x, so number of unknown here x. What I need to do? I need to minimize the potential energy associated with the system. So, system contains, look at this one, this is one pair, this is another pair, and this is third pair, 2 at a time, right. So, if I want to write potential energy associated, so potential energy associated will be, for these two if I write, these two I am writing, right, these two, K 2Q, Q divided by x, right. So, these two over these two over. Now, for these two I can write, for these two I can write plus k 8q into q divided by 9 minus x. So, these two over what is left? This one. So, this combination is left. Let us write for that. Plus k 2q 8q 2q 8q divided by 9. If I am considering x in centimeter, then everywhere it will be into 10 to the power minus 2, convert into meter SI unit, into 10 to the power minus 2 into 10 to the power minus 2. Now, question is, I want this value to be minimum. What is the condition? So, what I can do, I can use the concept of maximum minima. So, potential energy is minimum, du by dx has to be 0, right. So, I will equate this quantity to 0. Now, if you simplify, what you will get? This term is constant, its differentiation is 0. Here this will become 1 upon x square with 2. So, after simplification I am writing. So, this k after differentiation you have to equate it to 0, these all term will go right on other side 0. So, I am just writing the first term will be q 2 divided by x square with minus sign, then second term this term that will be plus 8 divided by 9 minus x whole square. Anyway this term is 0, constant term, no x is coming, and this I need to equate to 0. So, I can easily simplify this one. You can see that this term will go on other side, this will become 4 will come this side, right, and if you simplify, what you will get? 3 you will get this side, and after simplification you will get x is equal to 3 centimeter. That means to have minimum energy associated with the system, I need to place this q at 3 centimeter from here, right. So, I hope application of the formula k q1 q2 divided by r is clear. So, if there are multiple charges in the system, then we make pair and we write the energy associated with all the pair and add them, because energy is a scalar quantity, directly we can add, right. Let us see another example. So, consider the configuration of the system of 4 charges, each value plus q. Find the work done by the external agent in changing the configuration of the system slowly. Work done by external, first I am asking, work done by external, right, and it is also given that the change in configuration must be slow. So, there should not be any change in kinetic energy associated, right, from configuration 1 to configuration 2. So, from this configuration to this configuration, if you want to change, how much work we have to do, right. So, work done by external agent is equal to change in potential energy if there is no change in kinetic energy. So, change in kinetic energy is 0, change in kinetic energy, this is kinetic energy is 0, then only external agent, whatever work he does, that goes in the form of change in potential energy of the system, right. So, what is the initial energy of the system? So, you can see now there are 4 charges, right? How many combination you can make? So you can see here we have got one combination first, right, second, third, fourth. This way I can make 4 combination, right. Now this will make combination with this one and this will also make combination with this one. So altogether I am getting 6 combinations, right. So I write the potential energy associated with all the combinations, right. So let us first write these 4. So whatever be the energy associated with this one, same expression will come for this one, same expression will come for this one and same will be for next one, right. So I can multiply this to 4 directly writing. So potential energy in initial is equal to K Q1 Q2, that will become Q square divided by separation A, and how many such combination we are getting? 4. So I can write 4 here, right, plus there are 2 combination left. So I will remove this one as I have already written. Now let us see remaining. So those which are at diagonally opposite point, they are also making combination. So there are 2 such combination, right. If this is A, this is A, this will be A root 2. So I can write here K Q square divided by separation root 2A. There are 2 such combination, I will multiply it to 2. Now initial I got. So initial configuration had this much energy. Let us see final one. So same way I can let us first see the configuration. So same way I can make the pair first, second, third, fourth. These 4 combination I can make this way. Let us first write, and then what I will do, that these 2 and these 2, right. So same way I can write it, that final potential energy is K Q square divided by, if this is A, this is A, this will be, this distance will be root 2A. So I can write root 2A here and root 2A. And there are 4 such combinations plus, now diametrically opposite point combination. So K Q square divided by 2A, and there are 2 such combination, one is this one and another is this one. So I can multiply with 2, right. Now I have got initial energy, I got final energy, work done by external agent is equal to change in potential energy, and this can be written potential energy final minus potential energy initial. F stands for final, I stands for initial. You can substitute both the values, right. So initial I can substitute here and final I can substitute here, I will get work done by external agent. So you can simplify. After simplification, I hope everything is clear. Make the combination and write the initial energy of configuration, final energy of configuration, work done by external is change in potential energy, get the difference. So after simplifying you will be getting this one, right. So you can simplify, right. Now Let's see another example. So 8 charges of charge q and mass m are placed at the 8 corner of the cube of side A. So this is a cube and we are keeping 8 charge particle at 8 corners. Now what we want to do, we want to find out how much work done by external agent when this gap or edge length increase to 2a from A. So initially this edge length is A and I want to make cube of edge length 2a. So how much work I need to do, that is the work done by external agent, and how much work electrostatic force will do, right. So just now we have discussed work done by external agent. For that I require initial energy. So potential energy initial. Now there are 8 charge particles, how many combinations will be there, right. So look at the diagram, tell me how many combination it will be. You can see there are 12 edges. So there will be 12 direct combination. Adjacent one if I take, so adjacent one there are 12 edges. So there are 12 direct combination. So I can write K Q square, all are Q, right, Q Q Q A 12 times plus, so all adjacent one over. Now face diagonal, how many faces are there, total faces, front one, back one, this top one, this bottom one, this side one, leftward, and this one rightward. So altogether there are 6 faces, and for these 6 faces there are 2 such combinations, right. So these two will make one combination, these two will make one combination, right. So there are 6 faces. So let us first write energy associated with any one combination. So that is K Q square divided by, the separation will be, separation here and here will be root 2a, right. Every face will have 2 such combination and there are 6 such faces. So I have to multiply to 6 plus, so face diagonal over. Now look at the diagonals of the cube, how many such diagonals will be there. This one 1, then this one 2, then similarly this one 3, and this one 4. So there will be 4 such diagonals. So any combination if I take, for example if I am taking this and this, so the gap between these two will be, this distance is root 2a, this distance is a, so this distance will be root 3a. We can use Pythagoras, right. So for one such combination it will be kq square divided by root 3a, and how many such combinations are there, into 4. So this is the initial energy we are getting. Similarly we can find out the final energy. Now they are at separation 2 times a, so everywhere where I am writing a, 2a will come. So 12 K A square, Q square, this is Q, right, Q 2a plus 6 2k Q square divided by root 2 into 2a plus, so this a got converted into 2a, this a got converted into 2a, and similarly this will get converted into 2a. So, if I ask what is the work done by external agent, here I write work done by external agent, you have to just write final energy minus initial energy. If I ask what is the work done by field, then you have to write negative of change in potential energy in bracket potential energy final minus potential energy initial. So, substitute the value of this one and this one in the expression, you will get these two. So, you can see this is this whole, if I am considering 1 and this is just 1 by 2. So, after subtracting another 1 by 2 will come. So, if I multiply this to 1 by 2, I will get the final answer, right. Here I will substitute minus sign with this one. So, simplification work you can do. If you simplify, you will get this, right, work done by external, this one you can check later, and work done by field, electric field is this one, right. Now comes second part. See second part. If all charges are released simultaneously from rest, then find out their speed when they are at very large distance from each other. So, if I release, I was holding all these charged particle, now if I release, they will fly apart, right, they will move. So, as they move away from each other, their energy increases, right. So, they were just released, initial kinetic energy is 0. As they are moving away, their potential energy is decreasing. So, on the expense of decrease in the potential energy, kinetic energy will get increase. So, if I ask what would be the kinetic energy or what would be the speed when they are at infinite distance from each other. See, so first part is clear, now let us see second part. So, initial energy will remain same, so initial I will leave. Now there is change in kinetic energy. So, now I am solving second part. This B part. So, initially they were held like this and then system is released and all these particles reaches to infinity. So, when they will reach to infinity, their final potential energy will be 0. And according to work energy theorem, when I release, now there is no external force acting on the system, right. Only force acting on the system is electrostatic internal force. So, work done by external is not there, change in kinetic energy plus change in potential energy, right. Change in kinetic energy. So, if mass of each particle is m and assume that when they are at infinite separation, they all have velocity v. So, I can write each particle will have kinetic energy half m v square and there are 8 such particles. So, total kinetic energy will be this, right, 8 times half mv square, kinetic energy final minus initial, initially they were released from rest, right, plus change in potential energy final minus initial, finally they will have potential energy 0, right. I have calculated all these values, now I will substitute it here. So, final potential energy is 0 and initial you have written it here. So, if I take k q square by a out, okay. So, if I take k q square by a out, then this will be 12, first term will be 12, second term will be 12 by root 2 and then third term will be 4 by root 3, right, is equal to 0. Now, if you just simplify this one, then velocity will become, you can simplify, then velocity will become what? You can check, right. So, you can simplify this one and you can check, this is the answer of B part. and these two are answer of part A, right. So, I hope this example is also clear. Let us move to next one. Let us take one example when there is a motion. So, charged particle is moving, right. A particle B is projected towards a particle A from very large distance. So, we are projecting this particle towards this particle from very large distance. So, initially this separation is infinity, right, and say it is projected with some speed u, and it is given in the question ki find the minimum separation first case when A is held fixed. So, in first situation this particle is fixed, in second situation it is free to move, right. Now, so as this particle moves towards this particle, both are positive charge particle, it will experience force in this direction. So, as it moves from here to here, its speed keep decreasing. As its speed keep decreasing, at one point of time it will come to momentarily rest and then it starts moving in backward direction, right. That is why in question you are asked to find out the minimum separation, right. So, because of that electrostatic force, it will get deaccelerated as it moves, its velocity keep decreasing, and somewhere here it will come to momentarily rest and then it will move in backward direction. That will be the minimum separation. You want to find out the value of the minimum separation, right. Over here. And do how many unknowns? So, when this particle gets to this B particle gets to this point, so at that moment its velocity will be 0, right, and say this separation at that moment is V min. So, number of unknown is this R min, only one unknown. So, we require only one equation. You can solve this problem by Newton's law also. So, at any general moment you can write force on B and F is equal to mass into acceleration, you will get acceleration. You will get variable acceleration, right. So, one method of doing it is method 1. So, at any general position some r somewhere here, let us say this distance is r. So, when B is at some general position r, at that moment electrostatic force, I can write F is equal to K Q square divided by separation R square. So, this is the force it experiences, and because of this force the acceleration is divided by mass will give you acceleration, right. So, now you got acceleration and here you can write it this way, A is equal to V dV by dr. As velocity decreases, this is deceleration, we will put minus sign over here, and then this side I can write K Q square divided by M R square. So, I am using Newton's law in method 1, right. Now, you can see that you can easily simplify this one, dV is equal to minus K Q square divided by M R square dr integration limit. When it was at infinite separation, its velocity was u. So, separation infinity, velocity was u. When separation is minimum, at that moment we know velocity will be 0. I can integrate this expression and I can find out the minimum separation. This is one way of doing, right. So, using Coulomb's law or Newton's laws of motion, I can simplify this one or I can get the value of R min. Now, another easier method is using potential energy, because the integration part of field or force we have already done. So, we have already done this part, we can directly use energy method, without integration you will get answer. So, let us see second method, easier than this one. So, this is always little lengthy, because the acceleration what you are going to get, that will be variable acceleration. For constant acceleration we have seen some problem yesterday, right. So when acceleration is constant, we have the facility of applying v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2s. But when acceleration is variable, obviously you have to integrate the expression to get the result. So unnecessary it become lengthy. So for all such cases, as we have already defined the energy associated, it will be easy if you go by energy method. So let us see method 2. So now we will see method 2. Instead of Newton's law of motion, using Newton's law of motion, now I will use energy method. Procedure is clear. Now we are seeing method 2. So in case of energy, instead of talking about some intermediate position, I can directly jump from infinity to this point while writing energy. So I can avail the facility of skipping all the point when I am going by energy method. So method 2, let us see. Energy. So look at the situation once again. So initially they were at infinite separation. As there is no external work done by external agent, this is held fixed. If it is held fixed, that means the hinge will be exerting force on it. So on system, if you are considering this as system A and B, A plus B as one system, if you are considering this as system, on this system there is an external force acting, but that external force can change the linear momentum of the system. Force can change the linear momentum of the system, F is equal to dP by dt, but as this force is not doing work, it cannot change the mechanical energy of the system. What is the definition of work? Work done by external. So I am talking about the force coming from hinge. Work done by external is equal to force external dot displacement of point of application of force. So displacement of point of application of force, as it always remains stationary, there is no displacement of point of application of force. This quantity is 0. As this quantity is 0, work done by external is 0. As force is there, force changes the linear momentum of the system, but as point of application is not getting displaced, force is not doing any work. So as force is not doing work, I can conserve the mechanical energy. See, work energy theorem, work done by external is equal to change in kinetic energy plus change in potential energy. External is not doing work, so change in mechanical energy is 0, kinetic energy change plus potential energy change is 0. I can write this as kinetic energy final minus initial, potential energy final minus initial. Kinetic energy final minus initial, potential energy final minus initial. I will get all these terms this side. So final term I will leave on this side. I can write kinetic energy final plus potential energy final, and I will get initial this side, kinetic energy initial plus potential energy initial. So I can use this format, right? I can use this format. So what is the initial kinetic energy of the system? Initial potential energy of the system, that must be equal to final kinetic energy of the system and final potential energy of the system, right? So I am using this one. So I will erase all. I hope method 2 is clear. Let us substitute all the values. kinetic energy initial kinetic energy, this was held stationary, this was moving with velocity u. So, kinetic energy associated with that mass half m u square plus potential energy associated when separation is infinity, potential energy formula is k q1 q2 divided by r. When separation is infinity, then this r will be tending to infinity and this whole value will be tending to 0. So, initial potential energy associated 0, right, and this is what the reference we have taken, right. You can directly use that. Finally, what happens? Finally, it is not having any kinetic energy. So, final kinetic energy here, this will be 0 plus finally it will have potential energy. So, potential energy final is what? K q divided by r min, right. If you simplify, then this 2 will come here, mu square will come in numerator, sorry, this r min will come this side, 2 will come in denominator and this whole thing will come in denominator and this r min will be here, right. So, if you simplify, you will get mu square in denominator and kq square in numerator, right. So, concept of potential energy is clear. So, when particle is moving or system of particle there is a motion, then instead of going by Newton's law, using Coulomb's law, best way we can do is apply energy equation. By that we can avoid writing equation for all intermediate point, right. Directly we can jump from starting point to end point. Now, let us see next example or let us see next part of this one. If A is free to move, so if I release A, then what happens? As this moves, this pushes this one along the line joining. So, as this start moving towards this one, this also starts moving towards this one, sorry, this also starts moving towards leftward. So, what happens? As it starts moving from infinity with velocity v, then motion will be something like this. So, the gap between these two will get reduced. So, gap between these two will get reduced. There will be a point where the separation between them will be minimum and after that the gap start increasing further. So, what happens? Initially gap reduces, then gap increases, gap reduces and then gap increases. So, there is a condition in between where the separation between them will be minimum, right. Let us see. So, you have projected second particle when separation between them were infinity, this was infinity. Now, what happens? As it is free to move, this will also move. What will happen? Then after some time they both will have some velocity, right. The separation between them will be minimum when their relative velocity will be 0. Their relative velocity is 0 means they will have the same velocity. But if with respect to this one, this is having relative velocity in this direction, that means separation will increase. If with respect to this one, this is having relative velocity in this direction, then separation will decrease. If with respect to this one, this is not having any relative velocity, that means at this particular moment the separation is minimum, right, because from there onwards as it is pushing this one in this direction, its velocity will further increase, and as this is pushing it in this direction, its velocity will decrease after this event, right. So, as velocity of this one will be more afterwards and velocity of this one will be less, then separation between them start increasing. So, we are talking about the situation where separation is minimum So, the condition for minimum separation is their relative velocity has to be 0. So, you can see now we have got two unknowns. One is velocity, another is the minimum separation between them, right. So, we require two equations. In previous case there were only one unknown, what is the minimum separation. Now, in this situation there are two unknown, the velocity when the separation is minimum and minimum separation itself. So, I require two equations. Now, as there is no external force acting on the system, you can conserve the linear momentum. There is no external force acting on the system, whatever force acting between them is Coulomb force, that is internal to the system. This is pushing this one in this direction and this is pushing this one in this direction. If I am considering this system, this force will be internal to the system. So, on system, as there is no external force, linear momentum will remain constant, linear momentum of system will be constant, and as there is no external force on the system, mechanical energy of system will also be conserved. So, first equation I can write from conservation of linear momentum. You can see that initially system had the linear momentum mv or mu, this was stationary at that time, right. So, conservation of linear momentum, I can write m was moving with velocity u, and then finally what happens, m moves with velocity v and this 2m moves with velocity v. So, from this equation I have v is equal to u by 3. Now, I can conserve energy, conservation of energy. So, initial mechanical energy must be equal to final mechanical energy. Initial mechanical energy is kinetic energy half m u square plus initial separation was infinity 0, kinetic energy, potential energy is equal to final kinetic energy and potential energy. Now, both the particles are moving, half this 2m is moving with v, this m is also moving with v, plus they have got some finite separation k q, this will become q square divided by r min. Now, you can see if you substitute the value of v here, then you can find out the value of r min, right. So, previous case there was only one unknown, we require only one equation, we use conservation of energy. In this situation there were two unknown, we use conservation of energy and conservation of linear momentum because there was no external force acting on the system, right. Now, let us see another example. So, when you simplify this one, you will get 3k q square divided by mu square, you can check that. Now, see, question says particle B is projected towards particle A from very large distance with the speed u. Find the minimum separation between A and B if A is held fixed. So, this one is fixed and this B is not projected along the line joining. As B is not projected along the line joining, the force coming on B is not along velocity. Right. So, acceleration will make some angle with u. Previous case it was 180 degree. Now, in this situation it will be something lesser than 180 degree, it will be something like this. So, if I look at the number of unknown to see how many equations are required, so the path it follows because of repulsion offered by this one, it will be something like this. It is projected from very large separation. So, initially this separation is infinity. So, the path it follows will be something like this. It is start experiencing repulsion and it will be like this. So, this particle will follow path something like this. Right. What I do not know is the minimum separation. You can see that somewhere here separation will be minimum. I do not know this R min, and I do not know what is the velocity of B when it is here. So, again I have two variable or two unknown, you can see. So, R min and V is unknown. So, I require two equation. As this is held fixed, hinge will be exerting force on the particle. That means on system, on this whole system, there is external force coming, right. As there is external force on the system, you cannot conserve the linear momentum like what we have done in previous problem. You cannot conserve the linear momentum of the system because there is external force acting on the system at hinge. As force is not doing work, you can conserve the energy because point of application is not moving, you can conserve energy, right. So, you can conserve energy, but you cannot conserve the linear momentum. So, one equation conservation of energy, okay. Second equation, you can see that force on B will always be along the line joining. Right now if I see the force is like this, at some intermediate position this repulsive force will be along the line joining, it will be like this. So, you can see with respect to this fixed charge, this force is not offering any torque. As torque offered by the force is 0, we know that torque changes the angular momentum of the system, dl by dt, where L is the angular momentum, right. So, if torque is 0, change in angular momentum will be 0, and change in angular momentum 0 means angular momentum is constant, or I can say angular momentum of B about A is conserved. So, first equation I can write conservation of energy, and second equation in this situation I can write conservation of angular momentum, right. So, let us write both the equation. Let us first write conservation of angular momentum. Conservation of angular momentum. See, initial angular momentum, formula of angular momentum is for particle it is mr cross v. So, this is always written about point. So, in this situation it is about A. So, about point A of angular momentum of B about A. So, this is angular momentum of B about point A, right. So, initial angular momentum, this can also be written as m r vector cross v vector into sin theta, right. V sin theta is nothing but component of velocity perpendicular to the r, or I can also write r sin theta. So, if say particle is moving in this direction and about this point I want to write, right. So, this is r vector, this is velocity vector. What I can do, either I can extend the velocity and draw perpendicular. This distance will be, if I extend this one, this angle I am calling theta. So, if this is theta, then this distance will be r sin theta. So, I can also call this r sin theta as perpendicular, r perpendicular. So, this can also be written as m r perpendicular v. I hope this point is clear. So, if I extend this one, this u, this d is perpendicular distance, this d is perpendicular distance, right. So, initial angular momentum I can write So, I hope this point is clear, this you must have learned in rotation, right. So, I am using this one. So, initial angular momentum is equal to final angular momentum. I want to write initial angular momentum is u, perpendicular distance is d, m u into d, and final angular momentum is m into v into r min, right. So, there are two unknown that we do not know velocity at this point, and this is unknown and this is unknown. So, second equation. So, this is equation 1. Another equation, conserving energy, right. So, conserving energy, initially they were at infinite separation. So, initial energy, initial kinetic energy 0, sorry, initial potential energy 0, infinite separation, initial kinetic energy half mu square. Finally, when separation is minimum, k q q q q k q q divided by r min plus kinetic energy at this moment half m v square. This is equation 2. So, from this equation you can substitute value of v in terms of r. So, you will get one equation, only one equation which will contain all r min term. Simplify, you will get the minimum separation, right. So, I hope application of potential energy formula is clear. Look at the path it follows. The path is complicated. If you want to solve this problem by force method, it will become very lengthy, but if you solve this problem by energy method, like you have to write all the energies initial and all the energies final without worrying about the path it follows. So, this makes the problem simple, initial and final, we need not to worry about the intermediate points, right. So, I hope application of potential energy is clear. Now, let us see the self energy, right. So, to form a system, till now we were talking about two particles separated by some distance r, right. Now if I want to make a sphere of radius r, hollow sphere or solid sphere, right. So let us first take hollow sphere, uniformly charged hollow sphere. So a sphere of charge q I want to make. I want to make this sphere. So what I need to do, I have to bring dq charge from infinity and keep placing and distributing over the surface. So bring dq, distribute over the surface, bring another dq, distribute over the surface. This way I have to bring total charge q from infinity and distribute over the surface. Whatever work I am doing, that will go in the form of potential energy of the system. Work done by external, if it is being done slowly, work done by external is change in potential energy of the system. So if I calculate how much work I am doing in bringing all the dq's from infinity and distributing it over the surface of hollow sphere, then I will get the energy associated with this system, that I call self energy, right. So I hope procedure is clear, right, how to reach to the self energy expression. So every time I am bringing dq charge, every time, say at time t, I have already distributed a small q charge on the surface. Now I am bringing another dq from infinity and distributing over the surface, right. So whatever work I am doing, I am just doing the charge from infinity till the surface, because after that the field line will be like this, and to move the dq charge, if field lines are like this, and some small part of that dq you are moving this way, then motion in this direction and force in this direction, you do not have to do work. In just sprinkling the charge over the surface, you do not have to do work, right. So you have to do work only in bringing the charge from infinity and placing it till the surface, right. So what we can write, see, so what we are doing, we are getting charge from infinity and bringing it to the surface, right, bringing it to the surface, and then we are distributing the charge. So once we distribute the charge, total charge will become q plus dq, total charge on this one will become q plus dq. Similarly, we will bring another charge and we will distribute it. So what I am saying, that whatever work you are doing, that increases the potential energy of the system. So you can see that every time you have to place the charge at the same distance r. So the energy associated, if I write, when from here to here I am bringing, right. So from infinity, initial potential energy associated will be 0, and when I get that at surface, then potential energy will be K q dq divided by r. Here number of variable, you have to keep the charge at always at distance r, the radius of the sphere, right. So, change in potential energy when I am doing this, final minus initial, finally this energy and initial 0, right. If I integrate, I will get the total energy associated. In that this K and R is constant, K, this is K, right, this is K, this K and R is constant, I just need to integrate the charge. And what I want to achieve? I want to achieve this, that final charge here become capital Q. So, I need to integrate this charge from 0 to capital Q, that is Q square by 2, upper limit minus lower limit, Q square, capital Q square by 2 will come, see. So, we are bringing the charge, placing on the surface and distributing over the surface uniformly, right. And then I need to integrate this charge. So, after integration I will get Q square divided by 2 times 4 pi epsilon naught, that I can write 8 pi epsilon naught. So, you can remember the result, the energy associated will be what? Q square upon 8 pi epsilon naught r, right. Similarly, I can make, instead of hollow sphere I can make solid sphere. Problem with solid sphere is, as I am bringing charge from infinity, I have to increase the radius also. So, charge will get increased and radius will also get increased. Let us see. So, self energy of hollow sphere is clear. If charge is uniformly distributed, it will be Q square upon 8 pi epsilon naught r. Now, solid sphere. So, uniformly we are distributing charge on solid sphere. So, assume till time t I have achieved this. What is target? I want to make a sphere where charge is uniformly distributed over volume let the total charge be Q. So, this is what I want to achieve. So, what I am doing to achieve this, I am bringing dq charge and placing over the surface, and this dq charge is placed on the surface in such a way so that the density remains same throughout. In previous case, visualize this situation, you have already placed some charged particles and you are bringing extra charge and placing it on the surface, every time you are increasing the surface charge density. But here our requirement is, in this problem or in this situation, our requirement is the density remains unaffected. So, we will bring the charge and place it in such a way so that density of volume charge distribution remains same throughout, right. So, let us see what we can do. So, we are bringing charge from infinity, placing it over surface, and then we are distributing that over surface, right. I hope this animation is clear. Let us see once again. So, we are bringing this dq charge at time t, till now I have achieved this. So, q charge is already there, I am further increasing the charge on the system and radius of the system. So, right now radius is say r, final radius I want to achieve is capital R, final charge on the whole system I want to achieve is q. So, what I am doing, I am getting this charge from infinity and then distributing it over the surface so that radius also gets increased by dr. right. So, same way I will bring another dq from infinity and distribute it further. I keep doing this till I achieve this particular radius and this particular charge, right. Now, so previous case radius was constant, in this case radius is also variable, right. The same way I can write, previous case this was constant, sorry this r was constant, capital R was there, but in this case you have to increase the radius also, so this r is also variable. Now, this I need to integrate, but the problem is this r depends on q or q depends on r. The relation I can find out, I can write, because I know that density should remain same, so q upon 4 by 3 pi r cube must be equal to small q upon 4 by 3 pi r cube, right. These two will get cancelled out. I can write q is equal to r cube into capital Q divided by r cube, right. If I differentiate this equation, then I will get the relation between dq and dr that I can utilize here, right. So, if I differentiate, I will get dq is equal to 3 r square dr into q divided by r cube. So, charge I can write in terms of radius, dq I write in terms of radius, and then I integrate it from, now everything you are writing in terms of radius, now limit must be of radius. After substituting limit from 0, initially nothing was there, from 0 to capital R you have to increase it. So, from 0 to capital R, if you increase it, after simplification you will get 3 q square upon 20 pi epsilon naught r. So, you can also remember this way, that is 3 q square divided by 5 times 3 by 5 times 4 pi epsilon naught r. It depends on you how you want to remember it. If you are convenient with this expression, remember this format. Previous case for hollow we got q square upon 8 pi epsilon naught r. In this case we are getting 3 q square upon 20 pi epsilon naught r. So, this is the energy associated with solid sphere. So, today we have talked about self energy of solid sphere and self energy of hollow sphere, right. So, in next session we will discuss few problem based on the self energy, and then we will start potential, right. I hope you have enjoyed today's class, right. Thanks for watching.